This is an article by Byte by Go coming from their newsletter, a crash course in Redis. So I've seen Redis used in the past practically as some kind of a cache or some kind of synchronization mechanism. This is where I've seen it used. So let's see the actual behind the scenes and see how it aligns with what I saw practically, which is being used mostly as a cache. So Redis remote dictionary service, from this we can also see that it's got some kind of a remote database, and interesting to see what is a dictionary. Is it just a key value or something more than that? So Redis remote dictionary service is an open source BSD licensed in-memory database. So it's an in-memory database, often used as a cache, message broker, or streaming engine. Maybe because it's so fast, then you can stream from it items. It has rich support for data structures, including basic data structures like string, list, set, hash, sorted set. So not only is it going to store some key values, it has support for actual data structures that we usually see in programming languages. And I think this is also what makes it suitable for cache, because in cache we might want to store a list. So it's going to be friendly for storing our internal data structures there. And probabilistic versus a database where you store for the long term, so you transform it into a table and such. And probabilistic data structures like Bloom filter, which is usually used to know if something is in a set, if an item quickly know whether an item is already in set, and hyperloglog, which is used for the cardinality estimation, how many items exist, unique items. Redis is super fast. We can run Redis benchmark with its own tool. The throughput can reach 100 requests per second, I guess, for a single node. Hopefully for a single node. In this article, we will discuss why Redis is fast in its architectural design. Great. This is exactly what we want to see. Why is Redis? What is its architecture? So Redis architecture. Redis is an in-memory key value store. There are several important functions. The data structures used for the values, the operations allowed on the data structures, data persistence and high availability. Below is a high-level diagram of Redis architecture. Let's walk through them one by one. So we see here that we have clients. It has multiple client libraries like Go, Java, Node.js, Python, C#. So it has client libraries for popular languages. It has some object mapping for frameworks like .NET, Spring, Node.js, and Python. I think this is because if you want to store, my estimation, you want to store string, then they need to map it to the string representation in Redis. Maybe, let's see. And also we see here operations that we can do. So we see that we can do operation on strings, on lists, on sets, and we have get, set, mget, probably multiple get, append, list push, list pop, list land, list move. So basic operations on data structure as if they are locally, only you do that on Redis. And on sets, you can add to a set, remove from a set, maybe cardinality of a set, and check if is member. This is probably the Bloom. And this is cardinality is probably the hyperloglog. Okay, and it has, as they said, the in-memory data structure. We see that it has the list set. It has some storage, AOF, RDB, they will probably discuss it. And it has all the high availability, replication, security, access control, data encryption, admin, configuration monitor. So it's a heavy thing. It's not just store or get. It has all the security, all the replication, high availability, and administration. Right. Okay, so client libraries. There are two types of clients to access Redis. One supports connections to the Redis database, and the other builds on top of the former and supports object mapping. So one for connection, just connect, and the other to actually do the object mapping. Redis supports a wide range of languages, allowing it to be used in a variety of applications. In addition, the OM, object mapping clients, libraries allow us to model, index, and query elements. Data operation. Redis has rich support for value data types, including strings, lists, hashes, etc. As a result, Redis is suitable for a wide range of business scenarios. Depending on the data types, Redis supports different operations. The basic operations are similar to a relational database, which supports CRUD, create, read, update, delete, get, retrieve the value of the key, put, create a new key, delete a key value pair. The data structures and operations are an important reason why Redis is so efficient. We will cover more on the later sections. In-memory versus disk. Redis holds the data in memory. The data reads and writes in memory are generally 1000 or up to 10,000x faster than disk, 1K to 10K faster than disk. Reads, writes, see the below diagram for details. So we have L1 cache, each one is 10 scale, L1 cache, L2 cache, RAM. So Redis is here at the top of the fastness food hierarchy, right? 100 nanoseconds. Then we have network SSD database. Okay. However, if the server is down, all the data will be lost. So Redis designs on-disk persistence. So it has an on-disk persistence, so data won't be lost. For fast recovery, Redis has 4 options for persistence. AOF, append only. AOF works like a commit log, recording each write operation to Redis. So when the server is restarted, the write operations can be replayed and the dataset be constructed. RDB, Redis database, RDB performs point-in-time snapshots at a predefined interval, AOF and RDB. This persistence method combines the advantages of both AOF and RDB, which we will cover later, or no persistence. Persistence can be entirely disabled if you just, This is sometimes used when Redis is used for cache or smaller datasets. Clustering. Redis uses a leader-follower replication to achieve high availability. We can configure multiple. This probably meant leader-follower. It's sophisticated words. This could mean that you write to a single node and the other nodes are used for read. Let's say we can configure multiple replicas for reads, to handle concurrent read requests. This is how you scale the reads. If you have many more reads, then you write to one node and all the others are reading this with eventual consistency. Means that originally they are not consistent. They do not have the latest data necessarily. These replicas automatically connect to the master after restarts and hold an exact copy of the leader instance. When the Redis cluster is not used, Redis Sentinel provides a high availability, including failure, monitoring, and configuration management. What do they mean when the Redis cluster is not used? Not sure, let's see. Security and administration. Redis is often used as a cache and can hold sensitive data. So it is designed to be accessed via trusted clients. So they have security in mind because you store it in cache, things in cache there. Inside trusted environments, Redis security model is responsible for managing the access control layer and authorizing the valid operations to be performed on the data. I think Redis is a good bet if you want cache and high performance and you want someone to manage it for you externally. If you want super low, even lower latency cache, I'm not sure you will need it, but if you will need it, then maybe memcached. Which can be less features, but probably higher throughput, but Redis in most cases should be enough. Redis also provides an admin interface for configuring and Managing the cluster persistence, replication, and security configurations can all be done via the admin interface. Now we have covered the basic components of Redis architecture. We will dive into the design details that make Redis fast. In-memory data structures. So what makes Redis fast? Redis is not the only in-memory database product on the market, but how can it achieve microsecond level data access latency and become popular choice for many companies? One important reason is that storing data in memory allows for more flexible data structures. These data structures don't need to go through the process of serialization and deserialization, like normal on-disk data structures do, so can be optimized for fast reads and writes. Key value mapping. Redis uses a hash table to hold all key value pairs. The elements in the hash table hold the pointers to a key value pair entry. The diagram below illustrates how the global hash table is structured. With the hash table, we can look up key value pairs of one time complexity. So we have a global hash table, and we look up something, we get the entry, and we get the value. Like all hash tables, when the number of keys keeps growing, there can be hash conflicts, which means different keys fall into the same hash bucket. Redis solves this by chaining the elements in the same hash buckets. Always we get to the basics. I mean, no one invents the wheel in a big way. We always get the same basics. When the chains become too long, Redis will perform a refresh by leveraging two global hash tables. Value types. This is an interesting, two global hash tables. When the change becomes too long, and then what? You search in both of them? Value types. Or maybe you hash twice. Hash into each global table and then you hash your value inside it, could be. Value types. The diagram below shows how Redis implements the common data structures. String type has only one implementation. The SDS, simple dynamic strings, list, hash, set, and sorted set all have two types of implementations. Note that Redis 7.0 changed list implementation to quick list, and zip list was replaced by list pack. So Redis has the data structures. This is like the abstraction, and then they have the actual implementation of the data structures. Beside these 5 basic data structures, Redis later added more data structures to support more scenarios. The diagram below lists the operations allowed on the basic data structures and the usage scenarios. These base data types cover most of the usage of a website. For example, geospatial data stores coordinates that can be used. A ride-hailing application like Uber, Hyperlocal calculates cardinality for massive amounts of data, suitable for counting unique visitors for large websites. Stream is used for message queues and can compensate the problem with list. So they have the basic data structures, then they have streams, geospatial, also support for geospatial, bitmaps, hyperlocal, and then Bloom filter and TDIJ, stop K, count, min, sketch. Big data algorithms they have here. So they have multiple levels of database. They support the basic ones like string, list, set. The regular, intermediate one like stream, these are more complex, geospatial, bitmaps, and the big data structures. Now let's look at why these underlying implementations are efficient. SDS, Redis SDS stores sequence of bytes. It operates, I think this was the string data representation, SDS. Stored a sequence of bytes. It operates on the data stored in a buffer array in a binary way, so SDS can store not only text but also binary data like audio, video, and images. The string length operation on an SDS has time complexity of 1 because the length is recorded in len attribute. The space is pre-allocated. This is important for SDS with free attribute recording the free space for future usage. This is the optimization. The SDS API is thus safe and there is no risk of overflow. Diagram below shows the attribute of the SDS. Header, free, length, and the actual buffer that holds the actual string and some metadata on it. Zip list. A zip list is similar to an array. Each element of the array holds one piece of data. However, unlike an array, zip list has 3 fields in the header. Again, it has a couple of metadata to assist in the optimization and performance. ZL bytes, the length of the list, ZLT, the offset at the end of the list, ZLN, the number of entities in the list. The zip list also has ZLEND at the end, which indicates the end of the list. In a zip list, locating the first or the last element is of one-time complexity because we can directly find them by the fields in the header. Locating because we know what's the length. Locating other elements need to go through the elements one by one and the time complex. Okay, I think we get the global picture. I'm not sure we need to go actually over all the data sets. We see, and actually it's ended here, so it's good. So let's briefly go to what we saw here. We see that Redis is some kind of a database server, but not standard database server that is used for tables and to store data at sea. It has some built-in data types like string, list set, hash set. It's highly optimized. It has some additional metadata fields. It's a full system. But you can choose not to persist things locally on disk, but it's a full system. It supports all the security, the high availability, the administration, everything. It can be high scale with replicas, with read replicas. It supports, as they say, up like 100K requests per second. Of course, this probably depends on what types of data, how much data you have. It's mostly a get set data for standard structures. You need to have a library of your language in your computer program. It operates on RAM access. And it has multiple data structures, as we have seen, with some metadata to assist. And this was probably one of the more important slides of which data structures it supports. So it supports some basic data structure like strings, lists, set, hashes, and intermediate like streams, geospatial bitmaps, and also big data, hyperlog, log, bloom filter, Kako. So this was the overview of the Redis database from Byte Byte Go newsletter, a crash course on Redis.